Hi and Assalamualaikum. I hope all of you are doing great and always be safe. In this video, we are going to explain and present to you about the UV-Vis spectroscopy. This video is prepared by Group 4 and the members are Amirul Akil, Tam Yikian, Lee Jiaying and Nur Hidayah. I hope all of you are going to enjoy learning this topic.
The first one is introduction of UV visible spectroscopy. The principle of UV visible spectroscopy is based on the absorption of UV light or visible light by chemical compounds, which resulting in the production of distinct spectra. Spectroscopy is based on the interaction between light and matter. When the matter absorbs the light, it undergoes excitation and de-excitation, resulting in the production of a spectrum. When matter absorbs UV radiation, the electrons present in it undergo excitation. This causes them to jump from a ground state, an energy state with a relatively small amount of energy associated with it, to an excited state, an energy state with a relatively large amount of energy associated with it. It is important to note that the difference in the energies of the ground state and the excited state of the electron is always equal to the amount of UV radiation or visible radiation absorbed by it. The matter then will fall back to the ground state and emitted some energy with a specific wavelength and then detected by UV visible spectroscopy. UV visible spectroscopy used to detect the chromophore of matter quantitatively and qualitatively when the matter undergoes N to pi star and pi to pi star transition. Actually, there are 6 transitions of electron, but only 2 are detected by the UV visible spectroscopy because the wavelength is in the region of UV visible range. When white light passes through or is reflected by a colored substance, a characteristic portion of the mixed wavelength is absorbed. The remaining light will then assume the complementary color to the wavelengths absorbed. This relationship is demonstrated by the color wheel shown on the right. Here, complementary colors are diametrically opposite to each other. Thus, absorption of 420 to 430 nanometer light renders a substance yellow, and absorption of 500 to 520 nanometer light makes it red. Green is unique in that it can be created by absorption close to 400 nanometer as well as absorption near to 800 nanometer. Due to its sensitivity, UV visible spectroscopy widely used in identifying the impurities in polymers such as residual, monomers, inhibitors, antioxidants, and so on. The next one is Beers-Lambert law. Beers-Lambert law states that there is a linear relationship between concentration of sample with adsorbance A, which enable the concentration of sample to be calculated by measuring its absorbance. This law is used to calculate the concentration of the matter in the sample by using the formula A equal to epsilon Cl, where A is an absorbance, epsilon is molar absorption coefficient or molar absorptivity, C is the molar concentration, and L is the optical path length. From this equation, the higher the absorbance, the higher the concentration of analyte in the sample.
Next, let's see how the UV-Vis spectrometer works. UV-Vis spectroscopy refers to the characterization techniques that measure the absorption of radiation by a material as a function of the wavelength. It measures the absorption of a beam of light after it has passed through a sample or after reflection from sample surface. This is the working schematic diagram of UV-Vis spectrometer. There are 4 basic components to a simple single-beam UV-Vis spectrometer. Here we have a light source, a monochromator, a sample holder, and a detector. The light source passes polychromatic radiation to monochromator. Monochromator converts polychromatic radiation into components, wavelength, or bands of wavelengths. It resolves polychromatic radiation into its individual wavelengths and isolates these wavelengths into very narrow bands. Modern instruments Use a prism or more often a diffraction grating to produce desired wavelength. Sample cell is a transparent sample container. The light passes through the sample solution in sample holder will be detected by a detector. The readout will act as a signal processor to display the signal. There are different types of cuvette in rectangular shape. Here we have glass cuvette, plastic cuvette, and quartz cuvette. These cuvettes will be selected according to different wavelengths required. While handling the cuvette, opaque sides are held while transparent sides are not being touched. Next is sample preparation. First, prepare a blank solution and transfer it to a test tube. Dissolve the sample in the solvent of choice. Next, transfer the sample to a volumetric flask and make the solution up to the calibration mark. Then, fill the cuvette about volume of 3/4 full. Fill a cuvette with blank solution and others with test solution. Blank solution is solution which has only the chemical solvent in which the solute to be analyzed is dissolved in. For sample run, the blank solution in cuvette is scanned first to get the background absorption as it must be subtracted from the absorbance of the sample. Next, place cuvette with test solution in machine and run the sample solution. The absorbance of sample solution is measured. We will record and then analyze the absorption peaks.
Before going through the examples, let's discuss how conjugation affects the wavelength for the maximum absorption observed. The main point for it is, the greater the conjugation, the longer the wavelength of maximum absorption. I repeat, the greater the conjugation, the longer the wavelength of maximum absorption. Then, conjugation from unsaturated chain has different effect from the molecule with aromatic benzene ring. Normally, a benzene ring has a greater conjugation effect than a CC double bond in straight chain. For example, in this picture, we can clearly see that the wavelength of maximum absorption increasing with the degree of conjugation, or increasing number of CC double bond in between the chain. The molecule with single benzene ring has a higher wavelength value of maximum absorption compared to buta-1,3-diene with 2 CC double bond. Notice that the addition of benzene rings to the molecule had caused a more significant increase in the wavelength of maximum absorption. Continue to the example of styrene and polystyrene. The wavelength of maximum absorption is observed at around 291 nanometer. Look at the structure of styrene. There is a conjugated system consists of a CC double bond and a benzene ring. This is said as conjugated system because there are delocalized electrons in the molecule result in a resonant effect. Next, try to look at this polystyrene. The maximum absorption is observed at a shorter wavelength around 254 nanometer. The CC double bond is opened up to connect with each other to form a polymer. The absence of CC double bond results in a decrease in the degree of conjugation in the molecule. From this, it follows the fact that the greater the conjugation, the longer the wavelength of maximum absorption. When the degree of conjugation decreases, then a new peak will be observed at a shorter wavelength. That's all for UV visible spectroscopy. Here, we appreciate your time and attention to watch the video. Thank you.